This time on Dr. White's Fun with Graphs, we are going to talk about edge coloring. So an edge coloring is different than a vertex coloring. Here we're assigning colors to the edges of a graph such that incident edges get distinct colors, where a pair of incident edges are two edges that have a vertex in common. So for instance, these two have a vertex in common, so they are different colors, red and blue. This edge is incident to a red edge and a blue edge, so it has to get color green. And we're going to discuss the minimum number of colors needed to edge color a graph. So as we saw, an edge coloring is where we assign colors to the edges so that incident edges get distinct colors. So this is a proper edge coloring and this is not. Why is this one not? Because here we have two red edges that share a vertex in common. So that's not a proper edge coloring. So given a set of colors, we want to use as few as possible. Chi prime of G is the minimum number of colors in an edge coloring. They call this the chromatic index instead of the chromatic number. So note this is not a derivative, it's just a notation. And so the goal is to find the minimum number of colors in a coloring of a graph, edge coloring of a graph, and how to actually find that edge coloring. And it's worth noting that here the reason why we had to have three colors is because this edge was incident to these two. So in other words, whenever you have a vertex with many edges, however many edges is at least the number of colors you need to color the edges incident to that vertex. So here we have a vertex of degree 3, so we needed 3 colors here. And this will give an idea for a lower bound at least, the max degree. The vertex of largest degree has got delta many edges and needs delta many colors. And you see that right here. So here's a theorem due to Vladimir Vizing that the chromatic index has a lower bound of delta of G, the max degree of the graph, and an upper bound of delta of G plus 1. So the lower bound is quote-unquote obvious. Whenever you have a vertex of max degree, each of its edges has to have a distinct color, because otherwise you have two incident edges of the same color, and so you need delta of G colors in order to edge color the graph. And so his theorem is that you could get away with just adding one additional color. The proof of that is actually quite challenging. If I remember correctly from my undergrad days, it takes 75 minutes to detail the whole proof. So we're not going to prove it in a 10-minute video. We're going to just focus on the special case where a graph is bipartite. So in general, this divides graphs into two groups. These are called class 0 graphs, and these are called class 1. And of course, it's a $1 million problem to distinguish between these. So actually figuring out, given a graph, which of these two numbers you need is actually really hard. But if your graph is bipartite, you can show that, in fact, the chromatic index is the max degree. In other words, max degree many colors suffices to edge color a bipartite graph. Please note, the fact that it's bipartite does not mean you get to 2 edge color, because bipartite is talking about vertex colorings. So for example, take this bipartite graph. We see that the maximum degree is 3. And so this tells us that somehow by the theorem, chi prime of G has to also be 3. And so let's actually try to construct the 3 edge coloring. So let's use red, green, and blue as our colors. And I'm going to color using markers instead of pens. And so, well, let's color this edge. It has to be colored something, so let's just color it red. Now let's color some edge that's incident to it. Say this one better be something like blue, and the other one better be something like green. Where in the other partite set we've got this degree 2, so let's color this other edge. Let's color it blue and see what happens. Oh, marker. And now let's look at this edge. So it's incident to 2 blue edges, so we can color it with red probably. Let's try red. And then these 2 other edges are both going to have to be green. And now finally we've got 2 remaining edges and 2 remaining colors, so let's just go ahead and use them. And here we go. A proper edge coloring of this bipartite graph using 3 colors. And so that's how you find an edge coloring. In general, you might get stuck, and so in a moment I'll explain what happens when you get stuck. So suppose you're trying to edge color a bipartite graph, and you now want to color the edge between U and V. Well, you look at the colors that are already in use at U. We see red and green are in use, and so we see, because of the degree constraints that you have degree many colors, there has to be a color available that's not being used, in this case blue. On the other hand, you look at V's endpoint and you see that some other color has to be available. In this case it looks like red. There's no red edge incident to V, and there's no blue edge incident to U. And so if you're lucky, these 2 colors are the same. So if there's a color available at both, then that's the color you should use, where note the definition of available is that there's no edge with that color incident to that vertex currently in this partial coloring, because we haven't finished it yet. So if there's an available color at both, so a color that's not used at either vertex, then that color is free to be used on that edge without creating a problem. But you use that color and that edge won't be incident to any other edge with the same color. So the worst case scenario is the case we're looking at right now, where the only colors available are different. So we can't color this blue because we'd be incident to a blue edge, and we can't color it red because we'd be incident to a red edge. So what do? So in the case where you've got 2 available colors at U and V, but they're not the same colors, well then what you want to do is you want to swap colors so that they do have the same color available. And so starting from V, because red is available at V but blue is not available, there has to be a blue edge incident to V. So take that blue edge, look at the other endpoint. Is it incident to a red edge or not? Yes or no. If it is, continue this path. Next endpoint, is it connected to a blue edge? Yes or no. Continue the path. And so create this blue-red alternating path until you can't go any further. So either it's going to end, in the case blue, and end on a red edge, or it's going to end on a blue edge. So you keep going until you can't go any further. And then you look at the possibilities. We note, of course, that because each of these vertices is incident to both a red and a blue edge, none of these vertices are U and V, so this is actually a path. Moreover, this red edge, if you end in a red edge, oh, I forgot the other case I want is if you end in a blue edge. It's worth pointing out that this blue vertex, this blue edge, cannot be incident to U because blue is available at U. And likewise, if you end in this red edge, then this vertex is in this bottom partite set. So this vertex also can't be U because then you would have an odd cycle. So the point is, when you create this blue-red path, it is a path, and none of the vertices on this path involve the vertices you started with. And so suppose you found such a path, we'll then swap the colors on this path in either of these 2 cases and see what happens. So you swap the colors only on this path, nowhere else in the graph, and you see that you still have a proper edge coloring because you haven't created any new incidences. Anything that was incident with this red edge is now incident with this red edge, so you're going to still maintain the property of being a proper edge coloring. And moreover, now if you look at the U and V vertices, that you were actually interested in coloring in the first place, you now see that the same color is available, blue. It's available in both cases. So now you can color this remaining edge. And so the idea is that if you can't color an edge, the reason why you couldn't color the edge is because the available list of colors is different between your two endpoints. And so you should take one of the endpoints and take an alternating path with those two colors, swap the colors, and now one of the colors becomes available to color the edge, so you can extend the coloring. And this proves that you can actually color a bipartite graph with delta many colors. The max degree is actually the minimum number of colors needed to edge color the graph. Vizing's theorem actually uses the same idea in its proof. It's just a lot more complicated, but it's the same idea of taking alternating colorings. You just have to do it in the right order because odd cycles actually become a problem. So this argument would fail if you're allowed to have an odd cycle, because this vertex could be you, and then you would run into difficulties. However, at the very least, now we know how to edge color a bipartite graph, and this one last step gives us a way to do it in such a way that we never get stuck. And so for the homework, you should be able to edge color all the possible bipartite graphs with the minimum number required. And so we should do so.